So there are definitely multiple ways to reduce radicals, but this prime factor method is the method that is the same across across square roots, cube roots, fourth roots, across numbers, across variables, so I love doing it. If I wanted to reduce the square root of x to the seventh, well, it's a square root. I need groups of 2. I need prime factors. Variables are easy to get prime factor trees for. The prime factor tree for x to the 7th is just a set of 7 x's being multiplied. So to reduce the square root of x to the 7th using the prime factor method, I'm going to form groups of 2. That's considered my prime factoring. Because the index is 2, I form groups of 2. Every time I get a group of 2, I get one of those out front. So when reducing the square root of x to the 7th, I'm going to get 1, 2, 3 x's out front from the 3 pairs, and everything else stays under. X times x times x that I put out front is x cubed, and this reduces to x cubed square root of x. That's the beauty of the prime factoring. Once you get it, you got it for everything. Although I can reduce radicals in my head. So if you start looking at this and you know what it reduces to because you can predict what's going to happen, be my guest. You don't have to show it work if you can reduce in your head. I always reduce in my head. I'm not going to do 14 because I just did something with a 7th power and a square root. I'll do 16 though. 16 wants me to reduce a cube root of b to the 11th. Let me make my prime factor tree. I need 11 b's. It's a cube root, so I'm going to form groups of 3. There's 9 b's, and then 10 and 11. So I've formed my 11 b's, making groups of 3 because this is a cube root. In front of my radical, every time I get a group of 3, I get one of those out front, and anything that's unboxed goes under my radical. And now I'm just going to do the multiplication. This is going to be b cubed in front of my radical times the cube root of b squared under my radical. You notice I kind of waved and didn't check. I'm not really sure of a good way to explain how to check these, unfortunately. Oh, yeah, I can think of one, but it has to do with fraction exponents, and it's not very pleasant. Not worth my time. Ugh. My phone's ringing, and I love getting texts, phone calls, not so much. And I got really tired of my ringtone. I've had the same phone for 4 years, and I thought I changed my ringtone, but I failed, and it's going off again. It's like, oh, I'm so tired of hearing that. Let me reduce 18. It's a 4th root, so I need 4 of a kind. I'm going to do a prime factor tree for w to the 7th, making a string of 7 w's. It's a 4th root, so every time I get 4 of a kind, I can get 1 out front, and anything that's not part of a 4 of a kind is going to go under. So in terms of reducing the 4th root of w to the 7th, I'm going to get a w in front of my radical and a w under my radical. Whoops, and w under my radical. Ha ha ha, almost messed up. 1 w in front for the group of 4. 3 w's under for the ones that are unboxed. My unboxed get multiplied and shoved back under. For an answer, this is going to be w times the 4th root of w cubed. I'm showing way more work than I expect you to show. The more efficient you can be, the better. I don't need to see, every single boxing if you could do some stuff in your head. Let me move down to 20. I need a prime factor tree for x squared. It's a cube root, so I need 3 of a kind. I don't get 3 of a kind. that means this can't be reduced. This is a reduced radical because the exponent is less than the index. So this can't be reduced. Or I can write it with a fraction exponent as x to the 2/3 power. That's rewriting it. It's not technically what we're considering reducing. Same issue with 22. 22 is a 5th root. To reduce, I need a box of 5 y's, and I don't get enough. So this can't be reduced. Sometimes this method is inefficient. If the exponent divides evenly into the index, it's more efficient to use that strategy for reducing. In problem 24, because the exponent of 6 and the index of 3, when you divide them, you don't get a fraction. That's the better way to reduce. The prime factor way for reducing is going to give the same answer. If I reduced by prime factoring, what I'm going to do is write down 6 y's and form groups of 3. I don't have any stray lefts over, so I'm not going to have a y under my radical, which means I'm not going to have a radical. My answer is just going to be the 2 groups of 3 multiplied, 2 y's multiplied, which is y squared. So I can be efficient. The strategy that we learned for dividing exponents is still an effective strategy, and it's the way I reduce if when you divide, you don't get a fraction. If you get a fraction, this is the way to reduce. So you want both strategies. Pick the one that is the best, because the dividing, when it works, is faster. Like 26, I could just go b to the 15 divided by 5 is b cubed. Because the dividing didn't give a fraction, that's the better way to reduce. It's faster and equally accurate. If the dividing gives a fraction, then this is the way to do it. So I can write down 15 b's forming groups of 5. And when you don't have an unboxed number, you don't get a radical left. So this is going to be b times b times b. No radical left because there's nothing that's unboxed. And b times b times b is b cubed. Same answer, better way to do it, the dividing. But you don't have to notice it. If you don't notice that, you could divide, doesn't matter. The boxing is fine. I'll pretend like I don't notice 27, I could do some dividing. In 27, I have to do 3 separate prime factor trees to reduce it. The b to the 4th I could actually do by dividing. So I'm going to do a prime factor tree for 50. See if it's reducible. 50 equals shift degrees, minutes, seconds. 50 is 2 times 5 times 5. When I go to write an answer to this, I'm simplifying the 50, the a, and the b to the 4th. The 50 is going to give me a 5 out in front of my radical and a 2 under my radical. The a, there's not enough of them. It's going to stay under my radical. The b, I actually could have divided the exponent of 4 times 2 and got a b squared outside the radical, but I'll pretend I didn't notice that. Make boxes of 2 because it's a square root. This gives me a b and a b out in front of my radical, which is a b squared. It would have been better because I didn't have any strays if I just divided the exponent to get a b squared out front. The answer to 27, I'm not sure why I did 27 other than 28, other than I'm falling asleep and just lost focus. Need my afternoon nap. It's been a long summer. This has been just a monster amount of work. 30 is a cube root. I need to do each variable separately. So do a prime factor tree for 54. Whoops. Prime factor tree for 54 is 2 times 3 times 3 times 3. It's a cube root, so I'm going to get a 3 out front and a 2 under. The x, there's not a 3 of a kind. It's already kind of as prime factors as it can be. It's going to remain under my radical. The y to the 6th, much better to divide the exponent of 6 by the index of 3. And I'm going to get a y squared out in front of my radical. I could have made boxes and got 2 boxes of 3 and wrote a couple of y's out front. The z to the 7th, 7 divided by 3 is a fraction. I'm not going to divide and leave myself a fraction to tend to. So the z, I need the prime factor tree. For the z's, I'm going to get 2 z's out front and 1 z under. For an answer, 3y squared times z squared times, oh, yes, I did it right, times the cube root of 2xz. Let's do 31 together. 31's a square root. I need a prime factor tree for 32. 32 is 5 2's, I think. 32 equals, shift quotes, yeah, 5 2's. 2 times 2 times 2 times 2 times 2. This is a square root, problem 31. So I form boxes of 2. There's already a 4 out front. I'm going to leave that 4 out front. And I'm going to bring 2 2's out front and leave a 2 under. My computer decided to just spool up. I don't know what the heck's going on. The x is going to stay under because there's only one of them. And for the y cubed, it's a square root, so I'm forming groups of 2. I'm going to get 1 y out front and 1 y under. Let me multiply these 4 times 2 times 2. That's going to give me 16, along with the y in front of my radical, and then the 2xy under my radical. Haven't been checking all through chapter 4. Hopefully my videos aren't loaded up with awfulness. Let me do 34 and 36, and that's the end of the section. How about we do 34 and 35? I skipped 36. So for 34, I need to separate the 106 in my mind and the b to the 8th. I'm going to separate each one separately. The b to the 8th, because the index is 2 and its exponent is even, it simplifies to b to the 4th. Not under any old radical, but in the denominator. So in the denominator, I won't get a radical because I can divide the exponent and not get a fraction. Prime factor tree for 106. 106 is 2 times 53. There's no pairs. 106 is a reducible, non-reducible radical. My answer to 34, numerator doesn't reduce, the whole radical stays. The denominator, the entire radical disappears. 35, I'm going to work on the cube root of 81, x to the 5th, x, y to the 5th, and the cube root of 8 separately. Cube root of 8, I know, it's a perfect cube root. Shift cube root of 8 is 2. Just like in problem 34, my denominator is not going to have a radical. It's a perfect cube, or a perfect square root up there. I'll do the prime factor tree for 81, my prime factor tree for x, my prime factor tree for y to the 5th. 81 is just 4 3's. So I'm going to get 1, 2, 3, 4 3's, form a group of 3. In the numerator, I'm going to get a 3 in front of the radical and a 3 under my radical. The x is going to stay under my radical because there's not enough of them. And the y to the 5th is going to break up, so I get 1 y out front and 2 y's under my radical. For an answer to 35, in the numerator, I'd have 3y times the cube root of 3xy squared, and the denominator is just 2. There's no reductions I can do. I'm just done. And we will call this done. This is an important skill. And the next section is the imaginary number section. I don't think it's going to be that bad, and it should be quickish too.